Welcome back. So we're going to start off by implementing depth-first traversal of a graph two ways, recursively and iteratively, but first we're doing the recursive version. So I have a more detailed bit of pseudocode after this, but here's sort of the basic explanation. So define your function, your method, DFS, or you might want to call it DFS Recursive, so that you could do both iterative and recursive. And it takes a vertex to start from. There is no automatic inherent start point like a tree. So let's say you would pass in A. So we need to have a base case when we're doing something recursively. If you haven't seen the recursive section, you definitely want to check that out first. Otherwise, this will make no sense. So our base case is when vertex is empty. So the first time around, that's not going to be the case because we're passing in A or B or some starting point. If that is the case, we return something, return null, just get out of there. Otherwise, we're going to have a list of results. So we're building this array to return at the very end. So we add the vertex to the results list, meaning we've visited it. So we would add A in. And then we mark vertex as visited. So what would we do to actually mark it as visited? I'm just going to do something like this. Have an object, key value pairs, and when we visit F, for example, we add F in here and set it to be true. You don't have to do this. You don't have to set it to be true. You could use just another array and add A in there, but I like this approach. It's more explicit, and it also later on would allow you to mark something unvisited. If for some reason you wanted to, you could set it to be false, but it doesn't really matter. But this is how I'm going to do it. So mark it as visited. Then for each neighbor in that vertex's neighbors, so for all of A's neighbors, if that neighbor is not visited, recursively call DFS on that neighbor. So we would call depth first search on B and on D if those are the two neighbors. And then for each one of those, we do the same thing. We add it to the results list and then we mark it as visited. We would add it into here so that we don't visit it again. We don't duplicate our work. We don't get stuck in a little loop, which I'll show you that is possible if you don't mark things as visited. And then we visit each of its neighbors. But when we do it recursively, the way that these things are ordered on the call stack, I'll walk through it in the solution video, we end up with a depth-first traversal. So a couple things. Here's the same explanation as before. I'm going to just move through this very quickly. We see that this is the adjacency list representing this graph structure over here. And what we'll do is as we visit A, we're going to start there, I'll add it to my visited object, key value pair. And anytime, let's say we're looking at C later on, we would check, all right, which of its neighbors do we have? So we have C, all right, well, we have A, and we'll look at A. Oh, it's already visited, so we're not going to do that. Anyway, so we start at A, we mark it as visited. So then we go to A's children, and we look at both of them. Has B been visited? Has C been visited? Well, B hasn't, so we're going to recursively call depth first search on B and on C. But because it's recursive, this is going to happen first. And all of B's neighbors will happen before we come back to C. It'll be waiting on the call stack. So then we go to B, we visit B, we add it to our list of our object of visited vertices. And we look at B and it has two neighbors. Well, for each one, we're going to check, has it been visited? Has A been visited? Yes, it has. So we're not going to recursively call it. D has not been. So we keep going, and you can step through this on your own, but this is the idea, where we're going to keep track of what's been visited. And each time through, we have this pseudocode for each neighbor in that one vertex's neighbors. Check if it's been visited. If it hasn't been visited yet, recursively call depth first search on it. So remember recursion, call the exact same function again. Now I'll show you the more detailed pseudocode in just a moment, but first I just want to show you this. This is the code with what we've already written that generates this graph structure. So if you do want to follow along so you can test if things are working correctly, it can be a little harder to, if you just make up your own graph, it can be harder to know if it's working because it's less linear than a tree. So it's harder to think through it, at least for me personally. So you could copy this code and have the same structure as me, the same graph, and you should get this same order. So as far as the more explicit pseudocode, the more detailed pseudocode, for the recursive version, write a function that accepts a starting node. And we'll just go with A for now, but don't make it implicit. Don't set a default. We pass in A. Then you're going to create an empty list, an array, to store the end result that will return at the very end. So this will store the order. It should be, A, and then B, and then D, and so on, if we're starting from A. create an object to store your visited vertices. So that's something like this, but it should start empty. Okay? Then the slightly trickier part. Inside of, you don't have to do it inside the same function, but I'm going to do it inside of it. Create a helper function which accepts a vertex. So what I'll probably do is name the outer function depth first search recursive. And then the inside I'll just call DFS. And this is the part of our logic that matches the pseudocode I showed you before. So this is the actual recursive function. This function just sets up like the array. It sets up the results that we'll return at the end. It first originally calls our recursive function because I don't know if you remember from the recursive section, we talked about helper method recursion, where sometimes you need some data to persist. So you can't just have one recursive function that calls itself. You might need an outer function. So that's the case here. Okay, so your helper function should return early if the vertex is empty. The helper function accepts a vertex. If it's empty, we're done. The helper function should place the vertex it accepts into the visited object, mark it as visited, and push it into the result the result array, our list that we return at the end. Then for that vertex, loop over all of its children, children's the wrong term, all of its neighbors, and for each one, if they have not been visited, recursively invoke the helper function with that vertex, this helper function. So we don't recursively call the main function, we recursively call the smaller helper function. And then we will, mark each one as visited, add it to the array, check if its children are visited, and keep doing the same thing. Then the important part at the very end, invoke the helper function here. So you define it, then invoke it with a starting vertex. So we set it on its way. And this inner function is going to be updating that results array, and it's going to be updating the visited object. Each time through, it will have access to that. And then at the very, very end, return the result array. This is what will have been constructed by these recursive functions. So we'll end up with A, B, D, blah, 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 if you use the same graph that I used. And again, you can create it easily by just copying this. All right, so give it a shot. Recursion can be hard, but I think I tried to write it out very clearly, step by step. But if you don't want to try it, just watch the next video. As I step through the call stack, we'll see how it works and why it actually is depth first. That's coming up next.